Hi, I'm Jim. Welcome back to my series on the fundamentals of lift for pilots. Today's topic is circulation. Now, I will say I don't think this is something that is essential for a pilot to understand, but it's a topic that comes up from time to time, and depending upon the source, you may have heard that lift is caused by circulation, or that circulation is a consequence of lift, or that it's just a old mathematical model that's not that useful anymore. But in any case, we'll take the time here and walk through it. We'll talk about where it comes from, explain how this theory works when applied to a wing, and what it is and isn't useful for. So this is an old theory. It even predates the Wright brothers' flights. Lanchester was studying ship's propellers. Kutta was studying Otto Lilienthal's hang glider data. And it's a way to model the flow and lift around an airfoil while assuming a friction-free or inviscid, incompressible fluid. Now, fluid dynamics can get really complicated and into really deep math really fast. And if you're trying to solve things on a pencil with a pencil and paper, you like to simplify things, and the assumption of an ideal fluid, frictionless or inviscid, incompressible, things like that, greatly simplifies the calculations you do, but the side effect is sometimes you get weird results. And one of the weird results you can get is that objects don't have drag, or that there's an infinite number of solutions to the flow around an airfoil, and you don't get very far. But by applying the concept of circulation, you can get valid results that come reasonably close to real life. And I'll show you an example of that. So to give you a more intuitive feel for this theory, I'm going to actually step away from the theory and modify this illustration by John Anderson from the Fundamentals of Aerodynamics. And what he's drawn is a magical mystery vortex that just appears, but we will substitute instead let's assume that this is our cylinder and it is rotating. And a rotating cylinder in the air, because air has viscosity, will tend to cause the air close to that cylinder to rotate in the same direction. And if you've seen this before, just bear with me for a minute, because it really is a point. If we take that rotating cylinder and we move it through the air, or we blow air past it, if it wasn't rotating, you would get a flow something like this. But when you move that rotating cylinder through the air, over the top of the cylinder, the rotation tends to add or reinforce the flow going past, so we get a faster flow over the top. Underneath the cylinder, the effect of the rotation is to slow down or retard the flow under the bottom, so we get a slower flow over the bottom. In front, it tends to deflect the flow upwards. The flow behind the cylinder is deflected downwards, and we get that sort of flow pattern. And if we slightly abuse Bernoulli's principle, we can say that the faster flow over the top must lead us to a lower pressure, and the slower flow underneath must result in a higher pressure. And that net difference in pressure is, of course, lift, right? Because you have low pressure on the top, high pressure on the bottom, a net upwards force. And this is more commonly referred to as the Magnus effect. And for a couple examples of that, here is a rotating cylinder. The pressure difference isn't as obvious, but you can see the deflection in the flow as it rotates. I'll let it run one more time. As that cylinder speeds up, it deflects the flow. And here's another example. This is a screenshot from a video by Peter Sripol. I'll put a link to this in the description, of course. He made a RC aircraft using spinning Kentucky Fried Chicken buckets instead of wings, and it flies. But to get back to our theory, we can't use a spinning cylinder here because this is a theory for a inviscid or without viscosity or without friction fluid, so a spinning cylinder would do nothing. So instead we have to introduce our mysterious magical vortex of some strength gamma, and obviously the stronger or faster that vortex is, the more difference in speed you have between the top and the bottom, and the greater the difference of speed, the greater the difference of pressure, and that's what leads us to this idea that lift is proportional to circulation. But what does this have to do with airfoils, and where does this magic mystery vortex come from? I'm glad you asked. So here's circulation applied to an airfoil. Same concept where you have a translational flow. We've got our magical mystery vortex. It's kind of stretched out a little bit to fit around the airfoil, but it's again the same concept. And when you superimpose or combine these two flows, you again get the flow reinforced over the top, making it faster, lower pressure because Bernoulli. And underneath, the flow is slowed down from the circulation. It opposes the flow. Slowed down, higher pressure, again Bernoulli. And that's all good, but we're still left with the question, why circulation? So let's take just a moment and look at the trailing edge, and we're going to assume that this is a theoretical trailing edge where the radius at the trailing edge is exactly equal to 0. It's a sharp radius. And I said before, when you're dealing with inviscid flow, there's a infinite number of potential solutions. One flow solution could be that the flow is going like this around the trailing edge. Okay. Well, when you have this radius here equal to 0, theoretically the velocity right there at that trailing edge where the air goes this way and then is suddenly going that way, the velocity at that point is actually equal to infinity. And that's a problem. So there's the Kutta condition that says that the airflow at the trailing edge must be finite. And what that means in practice, if this is our theoretically sharp trailing edge again, in practice it means that the airflow coming off the trailing edge has to smoothly flow and merge from the top and the bottom like that. And that's a reasonable expectation for a real airflow in flight. And by applying that condition, we find that there is exactly one level or one strength or one speed of circulation that works for any particular airfoil operating a particular angle of attack and air density and velocity. So given that lift is proportional to circulation and that there is one level of circulation that works for any given condition, we now have determined the lift for that airfoil under those conditions, and we have modeled our airflow in a manner that gives us reasonable results. So you can argue that circulation happens because of the requirement that the air behaves at the trailing edge, or you can argue that circulation happens because it makes the math work. Either way. This is Anderson's take on the circulation and the Kutta-Joukowski theorem. You can pause the video and read it if you want, but basically he's saying it makes the math work and that the circulation is a consequence of the lift. This is the Kutta-Joukowski theorem. If the math doesn't make sense to you, don't sweat it. But the definition of circulation is the line integral over some curve enclosing an airfoil times the velocity times the distance, or differential of the distance. That gives us the strength of the circulation gamma. And then the Kutta-Joukowski theorem says that the lift for any unit span is the density of the air at some distance away from the airfoil times the velocity of the air some distance away from the airfoil, essentially the average translation of velocity, times gamma, which is the strength of the circulation. But now that we have a definition of circulation, we know how much, we want to use it to determine pressure distributions and things. It's still difficult to calculate the pressure or flow rates around an arbitrary airfoil shape, but as it turns out, it is relatively easy, to calculate the pressure distribution around a cylinder with or without circulation. And we can take that pressure distribution and map it to the pressure distribution about an arbitrary airfoil. And this was a technique, back before computational fluid dynamics, and that's one of the reasons that the circulation theory has persisted so long. And to this derivation, to show that you can make this transformation, Abbott and von Donhoff take about 9 pages to do this using a bunch of calculus. When I say easy, I mean relatively easy. But in the end, when you take an airfoil, in this case a NACA 4412, and you do the calculation of the effects of circulation, this graph here on the right, the diagram on the left is that airfoil. The graph on the right, we have the percent chord, or the percent of the distance from the front to the back of the airfoil along the horizontal axis. Along the vertical axis is a normalized pressure indication. We get a calculated pressure distribution. It's the solid line. And if you compare that to the experimental data, which is this dotted line with all the x's, it's not far off, especially considering that we're neglecting viscosity. If you apply a couple fudge factors to account for viscosity, that's where you get these other lines here that are even closer to the actual result. So this was a useful tool that gave reasonable results in real life. Is it still useful? Obviously, modern computational fluid dynamics give better results. They account for viscosity. You can look at the boundary layer effects, transitions from laminar to turbulent boundary layers, flow separation, a lot of general flow things that the circulation theory doesn't give you. In my opinion, circulation is not a very intuitive approach, at least for pilots, for explaining lift. I think it's kind of hard to wrap your head around the idea that you have these two flows happening at the same time and they get added up and you're satisfying some strange mathematical condition. So I don't think it has a lot of value from that perspective, though you will find a lot of sources, particularly older sources, that say that lift is caused by circulation. Circulation, and then applying Bernoulli's theory to calculate pressures, gives you the impression that Bernoulli's equation is some fundamental part of what happens with respect to lift. And if you're going to explain lift, you have to include Bernoulli in it somehow. And then I think, again, my opinion, my hypothesis, is that once you got this idea in your head that circulation in Bernoulli is lift, and then you start trying to explain lift without resorting to circulation, you try to simplify the circulation, or you try to come up with alternate explanations for the velocity differences, that's where the wheels come off the car. That is, I believe, where a lot of the fairy tales out there regarding lift, equal transit, streamline squeezing, all that nonsense, I believe that's where a lot of that came from. So that's all I really have to offer. So that's my explanation of circulation. I hope you found it at least entertaining, and thanks for listening, and I'll catch you on the flip side.